In this series of videos, I will be discussing natural logarithm. But before I'm going to discuss natural logarithm as it is, I want us to take a common ground so that we understand what we are talking about. And I'm going to derive the irrational number e. Why? It is important because logarithm, as I've said before in my previous videos, logarithm is the inverse of exponential function. So if, for example, we have y is equal to a raised to x, that is an exponential function. And we know that inverse of that is y is equal to logarithm of x with the base a. Okay. To simplify, we have y is equal to 10 raised to x. That means the inverse of that is y is equal to logarithm of x with the base 10. We don't write it. Okay? But there is also a base e. So y is equal to e raised to x. That is also an exponential function. E is an irrational number. Okay? And the inverse of that is y is equal to logarithm of of x with the base e. But we don't use logarithm when we talk about base e. We're using ln of x, or the natural logarithm of x. That's why it is important for us to know what is that e, irrational number e. Okay, in your calculator you have ln and e as the inverse or the shift. So in order to find the e, we're going to start with a compound interest. And the compound interest is an exponential function. A sub n is equal to a sub 0 multiplied by 1 plus I raised to, or I'm going to use r instead, not I. It's better. I'm going to use r. Let's see, raised to t. Okay? So if, for example, I'm going to take a look at this example. Suppose $1,000 or peso or baht or yen is invested, or Swedish crown, for 1 year at a fixed rate of 6% per annum. Use your calculator to find the final amount or maturing value if the interest is paid. I'm not going to use calculator. We're not going to solve it. I'm just going to give you a pattern about it. But it's good. So annually should look like this for 1 year. Let's say our time is equal to 1. We're thinking about 1 year so that it is initial value. Then we have 1,000 multiplied by 1 plus 0.06. I hope you will not get disturbed by the music. It's a good music anyway. And it is raised to 1. If it's semi-annually, then we have a sub 1 is equal to 1,000. 1 plus 0.06, it should be pointer, not comma, divided by 2. We know that because it is semi-annually. But in the exponent, we need to multiply it by 2. Okay? And then if it's quarterly, then we have a is equal to 1,000 multiplied by 1 plus 0.06 divided by 4, because it's quarterly. But then again, exponent, we multiply it by 4. And then if we have monthly, then we have a is equal to 1,000, 1 plus 0.06 divided by 12 raised to 1 multiplied by 12. The question is, how about if it is compounded? continuously, then it will look like this. Continuously. I hope I spelled it right. Then we have a sub 1, still a sub 1 there, is equal to 1000 multiplied by 1 plus 0.06 divided by, it depends how it is, I will name it capital letter N, 1 multiplied by capital letter N. So to summarize, we have summarized that now. If it's compounded continuously, then we have a sub n is equal to a sub 0 multiplied by 1 plus r, because this is our r, divided by how many compound is that? Raised to t multiplied by n. That is what we did there. Okay, but we need to simplify things. Okay, we cannot just put n as it is. We don't know what n is that. So if we can multiply that, for example, if we have a, or 1 divided by a, is equal to r divided by n, then we can put it there. And if we solve n, if we multiply both sides of the equation by n, then we have an a, then we have 1 is equal to 1 times n multiplied is equal to ar. There you go. This will become 1, this will become 1. Okay, that's important also. If we put it here now, in our formula here, a sub 0, 1 plus, this will become 1 divided by a, but our n now is ar multiplied by t. That's it. Our point of interest now is this one. How about if we can put a value of a, 1 plus 1 divided by a raised to a, such that it will be a constant. That is what we're going to see, if we can do that. I prepared here. We will start with 10 with our calculator. I hope I can wake up my calculator. Now my calculator is awake. Then I have here, I don't know where to put. Oh, smaller. That. Okay. Then I have 1 plus 1 divided by 10 this time. I have parentheses there also. Raised to a, which is 10 this time. So, then you see that it is 2.59. Okay? If I'm going to, maybe it's alright to do this. Ah, we cannot do that. I thought I can give more space there. If I am going to copy the 5 number, or all the numbers there, 2.5937426. Okay, and then if we try another number, that is 100, I will put 0 there. I will put 0 there. Execute. It is 2.7704813829. Okay. Let's try more. 1000. That is 2.7716923932. If it's 10,000, maybe you can see now it is 2.718. If it's 100,000, I will not going to write it anymore. It's 2718, and then if we have 10 million, that's 1 million, 10 million, then it is 2.7182863. If I'm going to compare, let's try 100 million or 1 billion. 2 more zeros. That is, if we compare this number now with the base E, so if I'm going to put this way, shift raised to 1, that is my base now, it's almost the same. So if it is compounded continuously, we don't need to use this one, the green one. We can only express that as A multiplied by I is equal to A sub n is equal to A sub 0 multiplied by E raised to RT. The interest times time. And this is now an exponential function. And E is an irrational number. Okay? So in my next video, I will be giving some properties or laws of natural logarithm, but you need to remember that they are similar with each other. Maybe I'm going to give you also the graph of e raised to x, and y is equal to e raised to x, and y is equal to ln of x, natural logarithm of x. I will stay there. It's already almost 13 minutes. And I hope you learned something how to derive the irrational number e. And thank you for watching. I will be discussing natural logarithm next time. See you around.